Welcome to our channel, where we bring you the most interesting and informative content from around the world. Have you ever looked up at the night sky and wondered, why is space dark, even though the sun is so bright? It's a question that has puzzled humans for centuries. After all, Earth is bathed in sunlight during the day, and our night sky is dotted with twinkling stars. Yet, space itself remains a vast, black canvas. The answer lies in understanding the fundamental difference between Earth and space, the presence of an atmosphere. Our atmosphere, a delicate layer of gases surrounding our planet, plays a crucial role in scattering sunlight and illuminating our world. Imagine throwing a handful of glitter into a sunbeam. The glitter particles scatter the light, making the beam visible from all directions. In a similar way, our atmosphere is filled with tiny particles like nitrogen and oxygen molecules, as well as dust and water droplets. These particles interact with sunlight, scattering it in all directions. This scattered light is what makes our sky blue during the day and creates the vibrant colors of sunrise and sunset. Earth's atmosphere is more than just the air we breathe. It's a shield that protects us from harmful radiation, and the reason we see a bright blue sky. The atmosphere scatters sunlight. Blue light is scattered more effectively, making the sky appear blue. This effect also creates stunning reds and oranges at sunrise and sunset. To truly grasp the concept of scattering, picture a single ray of sunlight entering our atmosphere. This ray, composed of all the colors of the rainbow, encounters countless tiny particles in the air. These particles act like miniature mirrors, reflecting and redirecting the light in random directions. This process of redirection is what we call scattering. Now, here's the crucial part: different colors of light are scattered differently. Blue and violet light, having shorter wavelengths, get scattered much more than their longer wavelength counterparts like red and orange. Imagine a game of billiards, where the white ball represents sunlight and the colored balls represent different wavelengths of light. When the white ball strikes a colored ball, the energy transfer is more efficient for smaller, lighter balls. Similarly, blue light, being lighter, gets scattered more easily by air molecules. This preferential scattering of blue light is what paints our sky with its characteristic hue. As sunlight streams through the atmosphere, blue light gets bounced around like a pinball in a machine, filling our sky with its vibrant color. Sunlight, the lifeblood of our planet, embarks on an incredible journey from the sun's surface to our eyes. This journey, spanning millions of miles across the vacuum of space, takes a dramatic turn as it encounters Earth's atmosphere. In the vast emptiness of space, sunlight travels in straight lines, unimpeded by any obstacles. However, upon entering Earth's atmosphere, it encounters a myriad of air molecules, water droplets, and dust particles. This encounter marks the beginning of a fascinating interplay between light and matter. As sunlight collides with these atmospheric particles, it undergoes a process called scattering. Imagine a beam of light as a stream of tiny marbles. When these marbles hit an obstacle, they scatter in various directions. Similarly, sunlight, upon striking atmospheric particles, gets redirected and dispersed. This scattering is not uniform, it depends on the size of the particles and the wavelength of light. Section 5: The vacuum of space, where light travels freely. Space, unlike Earth, is a near-perfect vacuum. This means it's almost entirely devoid of matter, those tiny particles that make up our air, water, and everything we see around us. In the vast emptiness between stars and planets, there's virtually nothing for light to interact with. Imagine a single ray of sunlight traveling through space. Without any air molecules to scatter it, the light continues on its path, unwavering and undeterred. It's like a spaceship gliding through the cosmos, encountering no resistance. This is why stars, those distant suns, appear as pinpoints of light in the night sky. Their light travels millions of miles through the vacuum of space, reaching our eyes without being scattered or diffused. The absence of an atmosphere in space has profound implications for how we perceive the universe. Without air to scatter sunlight, the sky would be black, even during the day. Section 6. Darkness in the void, why space appears black. Space, despite being filled with countless stars, appears black to our eyes. This stark darkness is a direct result of the absence of an atmosphere in the vacuum of space. Without an atmosphere to scatter sunlight, there's no medium for light to bounce around and illuminate the void. Imagine yourself standing in a vast, darkened room. Even if there are light bulbs scattered throughout the room, if there's no air or dust to scatter the light, you'll only see the bulbs themselves, not the space between them. Similarly, in space, starlight travels in straight lines from its source to our eyes. While countless stars emit light, their vast distances and the lack of scattering mean that most of this light travels past us unnoticed. This is akin to shining a flashlight in a forest at night. You'll see the illuminated spot where the beam hits, but the surrounding trees remain shrouded in darkness. Section 7. Stars in the distance, shining bright, yet so faint. The stars we see in the night sky are colossal balls of burning gas, emitting immense amounts of light and heat. Yet, from our vantage point on Earth, they appear as faint pinpricks of light against the black canvas of space. This apparent faintness is a consequence of the vast distances involved. Light from even the closest stars has to travel trillions of miles to reach us. As light travels through space, it spreads out, becoming less intense. Imagine holding a candle close to your eye and then moving it farther away. The flame appears dimmer as the light spreads out over a larger area. Similarly, starlight, despite its initial intensity, diminishes in brightness over astronomical distances. Furthermore, interstellar dust and gas can absorb and scatter starlight, further reducing its intensity by the time it reaches us. Section 8. Earth's glow, reflecting sunlight from afar. Have you ever looked at pictures of Earth taken from space? Our planet, a blue marble suspended in the blackness, stands out as a beacon of light. This glow, visible from millions of miles away, is not Earthlight, but reflected sunlight. Just like the moon reflects sunlight to illuminate our night sky, Earth reflects a portion of the sunlight it receives back into space. This reflected light, a combination of sunlight scattered by our atmosphere and light reflected from our planet's surface, is what gives Earth its ethereal glow. Imagine shining a flashlight on a mirror in a dark room. The mirror reflects the light, illuminating other objects in the room. Similarly, Earth acts as a giant mirror, reflecting sunlight and making its presence known in the vastness of space. This reflected light is not only a testament to the power of our sun but also a reminder of the delicate balance that sustains life on our planet. Section 9. The moon's tail, a familiar example of light and dark. The moon, our celestial neighbor, shows the interplay between light, shadow, and no atmosphere. Unlike Earth, the moon has no atmosphere. This results in a stark contrast between light and shadow. The lunar surface appears dazzlingly bright during the day. Step into a crater's shadow, and you're in absolute darkness. Without an atmosphere, there's no indirect illumination. Section 10. Appreciating our blue sky, a gift from scattering. The next time you gaze up at the azure expanse of the sky, take a moment to appreciate the intricate dance of light and matter that creates this breathtaking view. Our blue sky, a constant presence in our lives, is a testament to the remarkable phenomenon of atmospheric scattering. Without an atmosphere, our sky would be as black as the night sky, even during the day. It's the scattering of sunlight by air molecules, those tiny particles that make up our atmosphere, that paints the canvas above us with its vibrant hues. Imagine a world without a blue sky. The sun, a stark white disk against a black backdrop, would cast harsh, unforgiving shadows. The world would feel alien and desolate, devoid of the soft, diffused light that characterizes our planet. Our blue sky is not just aesthetically pleasing, it plays a crucial role in supporting life on Earth. It filters out harmful radiation from the sun, regulates our planet's temperature, and even influences weather patterns. Section 11. Conclusion: the universe's duality of light and dark. The contrast between the brightness of Earth and the darkness of space highlights a fundamental duality in our universe. Light, the essence of energy and visibility, coexists with the vast emptiness of space, where darkness reigns supreme. Earth, enveloped in its life-sustaining atmosphere, basks in the scattered glow of sunlight, while space, a near-perfect vacuum, remains a realm of darkness punctuated by the distant twinkle of stars. This contrast underscores the unique and precious nature of our planet, a haven of light and life in the vast cosmic ocean. As we continue to explore the universe, unraveling its mysteries and searching for other worlds like our own, we gain a deeper appreciation for the delicate balance of factors that make Earth so special. Our blue sky, a symbol of life and vibrancy, serves as a constant reminder of the intricate interplay of light and matter that shapes our universe. Thanks for watching. Don't forget to subscribe, like, comment and share.